My talk today is crack nucleation in ice, historical review, and research challenges. First of all, I would like to thank John for inviting me to give this talk. I am currently at Singapore, Nanyang Technological University, and what I'm going to do is review some of the experimental data, and followed by theoretical models. And lastly, I try to see if what can be done in the future. Well, why do we study crack nucleation? I think it's for obvious reasons. Ice fracture, and generally includes nucleation, interaction, and propagation of cracks. And in yesterday and the previous talk, we have seen many presentations on ice structure interactions. Now, what I'm looking at is perhaps the initial stage, the crack nucleation stage. So I'm not going to talk so much about the strength of ice. I'm going to focus on nucleation of cracks. Of course, and all of us know that cracks can influence significantly the strength of structures, whether they are moving or they are stationary. And some of us may know that cracks in large ice sheets can actually influence climatic changes. Now, what is the crack nucleation problem? Here I have a typical scenario. You have a columnar grain ice, with the z-axis randomly distributed in the plane. So this is what so we have the z-axis randomly distributed, and typically we are interested in compressive load. Of course, in general, we also have to deal with multi-axial loading, including tension. So what are we interested in? We are interested in the crack nucleation stress, i.e., at what remote loading would cracks start to appear, initiate, from within the ice structure. So that is one of the fundamental questions that we need to address. Secondly, we may also be interested in where the cracks are located. Are they located within the grains? Are they located at the grain boundaries? Or is a mixture of locations within the grains and also on the grain boundaries? And we would also like to know the size of the cracks, the shape, and perhaps the statistics of all these things, statistics of location, the length and the shapes, and also perhaps the stability of the cracks. And we would also like to know how these crack characteristics depend on the loading, how fast we load it, and also perhaps the microstructural parameters, such as the grain size. We were also interested in the porosity if you are dealing with maybe sea ice. And generally, we will also be interested in the temperature effect on crack nucleation. So these are the things that I'm going to go through in my talk. Now, this is by no means exhaustive, of course. This is just a few examples of the works that have been done, experimental investigations. They have been done since I think before the 1960s. By Go, Singer, Khalifa, Piku, Gupta, and of course Weiss and Susan. I'm just going to kind of select a few of these data and present them to you. So this is basically a review. Okay? What I'm going to show first is a series of graphs, okay, or figures, showing us where the cracks are located and what kind of cracks they are. Okay? So what we have here in the first plot, we have on the y-axis the proportion of grain boundary cracks versus the total number of observed cracks in the experiments that were done, okay, versus the mean grain size. Okay, I think this is for freshwater ice, okay, in columnar grain ice. Okay. We can see that a large proportion of the cracks, okay, are located on the grain boundaries, okay, something like 90% or beyond 90%. Okay, and this slightly diminishes or reduces with the grain size. But I guess the main characteristic that we can draw from this this kind of experiments is a lot of the cracks nucleated were grain boundary cracks. Now this is another one which plots, okay, the grain boundary versus the total number of cracks versus the rate of loading. Okay. Here we have something like a slow rate of loading 10 to minus 7 to fast, okay, 10 to minus 2. So this is something like quite brittle behavior. Okay. Again, we can see that as the strain rate increases, there is a higher proportion of grain boundary cracks. Okay, so we have this strain rate dependence. Of course, this is conducted for various grain sizes. Okay, this is D equal to 3 millimeters, and can't see it well. Okay, and we have some dependence on grain size. Okay. Next one. On temperature, okay, so this plots, okay, the proportion of grain boundary cracks, okay, versus the temperature from something like minus 35 degrees Celsius to 0 degrees Celsius. Okay, again, the substantial portion of the cracks were located on the grain boundaries. Okay, we do have some transcrystalline cracks as well. Now, in the first few figures, I've shown you the location of the cracks as well as the nature of the cracks, the grain boundary cracks, and there were some transcrystalline cracks. Okay. Now, in the next few figures, I will show you some characteristics of the cracks, of the nucleated cracks themselves. Okay. So, on the y-axis, we plotted something called the log mean crack length. Okay, so this is some averages, log mean averages of these crack lengths versus, I guess D is the grain size. Okay, so we can see that for different strain rates, okay, 10 to minus 3, okay, 10 to minus 4, 10 to minus 5. So this is relatively fast rate of loading. Okay, and basically we can see that the crack size, the nucleated crack size essentially scales, okay, linearly with D in the log scale. Okay, I think this is in the log scale. Okay, so that means that if a larger grain size, you're going to get larger cracks. Okay, and if you look at the rate of loading, okay, it seems that the higher the loading, okay, for example, from 10 to minus 5 to 10 to minus 3 per second, you tend to get smaller sizes, okay, for these crack lengths. Okay. So all these were experimental reports or observations. I guess this is a similar thing. We are looking at the crack size or the crack length versus the strain rate, okay, and versus for various grain sizes. Okay. The higher the strain rate, in this case, okay, there is a tendency for smaller cracks, okay, to nucleate. Finally, the dependence of this crack length on temperature, okay, again from -35 to close to 0. Okay, you can see that the colder it is, okay, the colder it is, okay, the shorter the cracks. Okay, so this is what were experimentally observed. Okay, next, I'm going to show you the nucleation stresses themselves. Okay, previously I've shown you the locations, okay, as well as the crack lengths, but here we have some experimental data on the dependence of the nucleation stress in megapascal versus the temperature. Okay, you can see that the colder the ice is, okay, the higher the nucleation stress. Okay, something like maybe 3 times. Okay, from 2 megapascal to something like 6 megapascal. Now this were the experimental data of Khalifa, Jones, and Slade. Okay, you can see that this data were quite old. Okay, maybe close to 25, 26 years ago. Okay, and here we have some similar results. Okay, on notice that this is not necessarily the nucleation stress, but it's really the ice strength, okay, versus the temperature. Okay, here we have compression, and the lower graph we have the tension. Okay, now as far as the tensile loading is concerned, this is perhaps close to the nucleation stress, okay, which is relatively independent. The tensile strength or the tensile nucleation stress is relatively independent of temperature, perhaps from 1.5 to something like 3. Okay, this is the strength, okay, which I'm not going to talk so much about in compression. I have some more data which plots, in this case, the nucleation stress, okay, the initiation stress in megapascal versus the grain size to the power of -12. Okay, so basically, if you move down along this axis, okay, you get the d -12. Okay, so it's an inverse relationship. Okay, 1/d to the half, -12. Okay, you can see the data over here. Okay, so the nucleation stress increases, okay, with d to the -12. Okay, we have some model predictions over here. Okay, this was actually done by myself. Okay, back in 1990. Okay, which did not seem to fit the data of Khalifa quite well. Perhaps it was an overestimation or over prediction. Okay, I think this is in compression. Okay, and so I'm going to go back to this modeling issue in the next few in the next half an hour. So, and this is perhaps the work of Piku and Gupta in 1995, which plots the principal stresses, the principal stress, okay, in the vertical direction essentially versus confinement. Okay, so you have some lateral confinement stress. Okay, this is a ratio. Okay, so this is 10% of the principal stress, 20%, and so on. Okay, for 2 different strain rates, and not surprisingly, we can see that the amount of stress that you can place on the ice, okay, is going to increase, okay, with the level of confinement that you get laterally. Okay, so this is these were all observations. Now I'm going to review some of the physical mechanisms of crack nucleation that were developed to explain some of these phenomena. Okay, so I'm going to go over the dislocation pileup mechanism. Okay, the so-called elastic anisotropy mechanism, and there's some issue with the so-called precursors. Precursors are basically cracks, small cracks, perhaps, which exist, okay, in the ice microstructure before you load it. And I'm going to talk about the grain boundary sliding. And lastly, I'm going to talk about something which I am working on, the plastic anisotropy. Okay. Now, dislocations were observed in ice, okay, and all of us knew that. Okay. And the dislocation pileup mechanism was used to explain crack nucleation in metals, in metallic materials. Okay. And the ice mechanics people borrowed that idea. Okay. So, Zena, for example, analyzed the dislocation pileup mechanism and developed some equations back in the 1940s. Okay. And this is just one of the variations of the many models that were developed by these guys. Okay. You have a shear stress, a tau E, effective shear stress. Okay. You have a source of dislocation here and here. Okay. And the pileup is the obstacle is over here. Okay. So that is the source, that is the obstacle, that is the source, that is the obstacle, some sort of anti-symmetric arrangement. Okay. Now you can actually calculate the shear stress, okay, that is necessary to bring about, okay, the formation of a crack, okay, at the obstacles. Okay. So we can analyze the dislocation distributions, okay, which I'm not going to do, okay, and these were all contained in these previous works. Okay. Now let me introduce you to the idea of elastic anisotropy. Okay, as we know, this is the basal plane of the eye crystal, okay, and the eye crystal is elastically anisotropic, and it is not that strong. Okay, if you look at the CGS, which is the elastic constants or stiffness constants of this single eye crystal, you can see that 13.929 versus 15.01 gigapascal at minus 16 degrees Celsius. Okay, the difference between the two directions, okay, the stiffness between the two different directions is not that significant. Okay, this is just the inverse of the stiffness matrix. This is the compliance matrix. Okay, so that is the elastic anisotropy. So what? Well, Cole back in 1998, okay, proposed a model of crack nucleation based on this elastic anisotropy of a single crystal. Okay, so what we have shown here is two single ice crystals, okay, neighboring single ice crystals, okay, and they may have different basal plane orientations, okay, and under a remote loading, which could be tension or compression, and this single crystal and that single crystal, they are going to deform differently, okay, because, okay, the elastic property is not isotropic, okay, and I think his model is based on a strain energy calculation, okay, the strain energy stored in this grain versus the strain energy stored in that grain, and the difference, okay, causes the crack nucleation on the boundary. There was the line between these two grains. Okay, so there was the work back in 1988. Okay, now let's see what the predictions were. Okay, so this is Cole's predictions. Okay, the nucleation stress versus the grain size. Okay, now he showed that the elastic anisotropy mechanism, the stress is similar but somewhat higher than the pileup mechanism. Okay, and he argued that the dislocation pileup mechanism can be a plausible mechanism if you already have a sufficient number of dislocations present, okay, before you load the material. Okay, because if you wait for the dislocations to generate and pile up, it would take some time. Okay, maybe an order of 50 to 100 seconds. Okay, so that was his reasoning. Okay, that the dislocation pileup is possible if you already have a sufficient number, and that may be more valid if your rate of loading is small, and maybe 10 minus 6, 10 minus 5. Okay, this one I mentioned it before. Okay, the nucleation stress is slightly higher for the elastic anisotropy mechanism. Okay, they exhibit the same grain size dependency. You see, all of these models basically they all have this d to minus half kind of grain size dependency. Okay, especially if you use the fraction mechanics idea. However, the differences between tension and compression were not accounted for. Okay, so we cannot, this model, this simple model that was presented could not explain the difference, okay, between the higher compressive initiation stress, okay, versus the lower initiation stress in tension. Now, then back in 1990, and Samson-Du and Wu, okay, and tried to or attempted to work out a more detailed model based on this elastic anisotropy mechanism. Okay, so what we have here is we are looking at a pair of grains. Okay, but not in isolation. But this pair of grains existed within an isotropic matrix. Okay. So this is the ice matrix, okay. And specifically we are looking at two grains which share the same basal plane or the z-axis orientation. I guess this zeta over here, okay, which is the angle between the z-axis and the global z-axis. Okay, we call it the z-axis orientation. Okay. Now the essential idea about this model is we use fraction mechanics. We use LEFM. We use linear elastic fraction mechanics. Now, in linear elastic fraction mechanics, typically we deal with the existence of pre-existing defects, okay, and which we call a precursor. Okay, you can call it anything you want. We call it a precursor. Okay, precursor to a larger crack. Okay. This precursor lies on the grain boundary and is initiated from a triple junction. Okay, so using we can calculate on average, okay, the remote stress, of course, as well as any microstructural stress that was induced, okay, due to the elastic anisotropy between this pair of grains and the surrounding matrix. Okay, so we have. On top of the remote loading, we have what we call microstructural stress arising from, okay, elastic anisotropy. We combine this, linearly superimpose these stresses, and then we just use fraction mechanics idea. Okay, so we have some loading on this precursor crack, and we can of course predict the possible extension of the precursor crack, okay, either along the grain boundary or into the crystal. So that is the main idea. Now, before I critique this idea, I will just show you the results. Okay. So this is a plot that I show you, a similar plot I showed you before. Okay. This is the nucleation stress, either in tension or in compression, okay, versus the grain size, okay, from something like 2 to 10 millimeters. Okay. Now, previously, I showed you the prediction of coal, okay, pileup mechanism, as well as the elastic. Let's focus on the elastic anisotropy mechanism of the results of coal, which was based on basically the strain energy difference between two neighboring grains. Okay. Now, our prediction based on the elastic anisotropy and using a slightly more detailed model, okay, results in a higher nucleation stress. Okay. So this is a coal model. This is our model. Okay. However, our model shows a difference in prediction between compression, which is at the top, and tension, which is at the bottom. Okay. Now, why in our model could we predict a difference in nucleation stress between compression and tension? It's because we use the idea of friction Okay? So when the precursor is under uniaxial compression, for example, okay, the precursor faces rub against each other. Okay? So this resolved shear stress acting on the precursor crack was reduced, okay, by the friction. Okay? So you need to put more remote stress, okay, to overcome that friction. Okay? So that is the basic reason for an increase in the nucleation stress for compression, okay, over that in tension. Okay? Closed models, of course, he did not use the idea of friction, so there is just one result. Okay? This is just some more details. Okay? This one plots the nucleation stress versus the grain size. It's the same kind of plot, but for various basal plane orientations. You can see 90 degrees is zeta, which is the c-axis orientation. It's 90 degrees, we get a lower nucleation stress than if the basal plane orientation is 45 degrees. Okay, we have some, I would say, a rather widespread of data or results. Okay, if the c-axis orientation changes. Okay, this broad spread of nucleation values is higher or is broader in compression than in tension. Okay? So these results that we see below here refer to the tension results. Okay? So this is 90 degrees to 45 degrees. Okay? Let me see what is this. Okay, we use the concept of this precursor, right? So the precursor has a length of 2a. Okay, so we use 2a over d. D is the grain size. Okay, 2a over d is 0.1, and we compare the results for 2a over d equal to 0.05. Okay, and of course, if you assume a lesser or a smaller precursor, okay, your nucleation stress is going to be higher. Okay, so this is all expected. Okay, this is for compression. I guess this is for tension. So this basically shows us the variability of the predictions if you change some of your model assumptions. Okay? And this is changing a 2a over d assumption, and this is like considering the possibility of having a random c-axis orientations within the polycrystal. We also did some analysis on crack nucleation for the multi-axial stress state. Okay, so this is if you look at this axis, basically sigma xx. Sigma xx is the vertical direction. Okay, and on the vertical axis, sigma gz, sigma gz is basically the horizontal direction. So this is vertical and this is horizontal. So for uniaxial loading, you can see that the compressive stress is the order of minus 2.5 megapascal. Okay, if the grain size is maybe 5 millimeters. Okay, if you have a smaller grain size, okay, d equal to 1 millimeter, the uniaxial compressive stress is higher, maybe something like minus 5.5. Okay, so this is the tension region. If you have biaxial tension, okay, so this region is something like tension compression, and this is biaxial compression, okay, and so on. Okay, so we did some analysis on the dependence of crack nucleation on the multi-axiality of your loading. All this is pretty straightforward because we use the concept of linear fracture LEFM. Now let me just discuss some of the reservations or criticisms that we have, and let's see how we can overcome this. One of the observations that has been made was dislocations require time to nucleate and pile up. Okay? Maybe longer than the time cracks were observed to form. Maybe if you did some calculations, okay, and assuming it is a dislocation pile-up mechanism, okay, of course that depends on the mechanics of the motion of dislocations. Okay, and the cracks that were observed to form experimentally, okay, they could occur within maybe 10-20 seconds. Okay, but if you assume a dislocation pileup mechanism, maybe it would take longer than that. Okay, so there was some argument that this mechanism works only for a very slow rate of loading, in which the dislocations, the time required for the dislocation to pile up, okay, there will be sufficient time. Okay. The temperature dependence on the nucleation stress. I guess this is not very well investigated, at least from perhaps from the modeling point of view. Okay, it's not well accounted for by, at least by the elastic anisotropy mechanism. Okay. We all know that, of course, the elastic constants of ice also change with temperature. Okay. But that change is perhaps not that significant. Okay. If you look at the data that I showed you earlier, the nucleation stress, okay, for ice at close to freezing temperature is something like, maybe 2, and at minus 40 degrees Celsius, maybe something like 6. Okay, it's 3 times. But the elastic constants of ice did not change 3 times. Okay, over that temperature drop. Okay, so there's some issue about the regarding the temperature dependence on the nucleation stress, and how do we model this this dependence. Okay, and lastly, okay, there were some questions about observations of the assumption of the existence of precursors. Okay, 2a over d 0.1. Okay, is pretty large, I guess. Okay, because d is something like the order of 1 millimeter, 2 millimeters. Okay. So if there were precursors, maybe we can observe them. Okay, and list, okay, in experimentally grown ice. Okay, for real ice in Asia, I don't know. Okay, for real ice in Asia, maybe this assumption of precursors is valid. Okay, because you cannot have perfections. Okay, so we have some of these criticisms. Okay. So the next thing we did was try to analyze, okay, the elastic anisotropy mechanism at an even greater depth. Okay. The previous work, we basically assumed that we can calculate the microstructural stress. Okay, but nowhere did we address the issue of crack nucleation due to the microstructural stress alone. In other words, we already assume the pre-existence of a precursor crack. Okay? We do not really explain how these precursors came about. Okay? It could be already there because ice in nature was not perfect. Okay? But in laboratory grown ice, maybe you did not see these precursors. Okay? So perhaps we need to look into this in greater depth. Okay? So we follow the so-called a complete SLB procedure to look at the stress concentrations that could arise, okay, in the vicinity of triple junctions, okay, of grains that have random z-axis orientations. Okay. So anyway, what is this about? Okay, so we look at in this procedure. But by the way, this procedure is used to calculate the stress concentrations. Okay. So we isolate a number of grains, in, for example, 1, 2, 3, 4. Okay. So we have 4 grains, okay, within the polycrystal, and under some loading, it could be tension, it could be compression, okay, or any loading. Okay. Now the procedure requires us to, first of all, remove these 4 grains, the P grains, like this, and subject each of them to the remote loading. Okay. So you let these 4 crystals grow, okay, unconstrained. Okay. Okay. So the deformation of each of these crystals, okay, P equal to 1, P equal to 2, 3, and 4, would be equal to the crystal compliance times the remote loading. So this is the unconstrained deformation of each of these crystals. Okay. Then, but overall, as a polycrystal, okay, the strain is S tilde, okay, S tilde times sigma infinity. That is the polycrystal strain. Okay. S is basically the average elastic constant or elastic compliance, okay, of the polycrystal. Okay. So if you take away SP sigma from, okay, the average strain of the polycrystal, okay, you get a misfit strain. Okay. So each of this, okay, very subject to epsilon P, could not be put back into the polycrystal because they have some misfit. Okay. So in order to remove or to eliminate that misfit, we need to apply certain stresses, okay, which you can call them microstructural stresses if you want, and I think indeed we call them microstructural stress. Okay, we just multiply this misfit strain by the polycrystal stiffness. Okay, so that is a misfit stress. Okay, but how do we apply this misfit stress on these crystals? Okay, we have to basically apply the attractions. Okay, this is just the dot product between the normal vector to each boundary, okay, and the misfit stress. Okay, so these are the tractions TPQ. Okay, so P is on the crystal, Q is on each of the boundaries. Okay, 1, 2, 3, 4, maybe 6 or 7 boundaries. Okay, so we need to apply these tractions so that, okay, they can be fitted back into the polycrystal without any, nicely, okay, without any misfit. Okay, but now the problem is after the reinsertion, okay, we have these tractions which apply. Okay, so we need to relax these tractions. Okay, so we need to apply tractions opposite to what we applied to the crystals previously. Okay, so this is a relaxation procedure. Now, in the earlier model of Sundar and Wu, we did not consider this third step. Okay, these relaxations. Okay, we basically stopped somewhere here. Okay, we stopped exactly here. Okay, so here. This will give you, at least in principle, according to the SLP procedure, a complete, okay, calculation of the microstructural stress. Okay, and we can see that there will be some singularities arising. Okay, because we have these corners over here. If you look at of course I skipped some of these details. Okay, if you look at these tractions, they will induce singularities at the edges of the segments over which they act. Here, I'm just going to quickly go over some of these results. Okay, we consider something like 208, or maybe I think it's 208. I forgot. Grains. Okay, just now in the illustration, I isolated 4. Okay, you can isolate 4, you can isolate 5, or you can isolate 200 or whatever. Okay, number of grains. Okay, and perform the SLP procedure. Okay, now these numbers that you see within each grain refers to the C-axis orientation. This is 170 degrees, this is 90 degrees, 127, 270. Okay. So we use a random number generator, okay, to assign arbitrarily a C-axis orientations for each of the 208 grains that we analyzed. Okay. Let me just go over one of this. Okay. The essential idea of this is if you look at one particular combination, okay, from the lot, okay, this is 67 degrees, okay, the C-axis is 6 degrees, 64, okay. Now I'm going to change the C-axis orientation by a small amount, that which I call delta 01, okay, something like this, okay. You can see the microstructural stress, sigma 2, I think this is the stress normal to the grain boundary, okay, and how they change, okay, as the C-axis orientation changes, okay, and I guess the change is not that significant, perhaps, okay, maybe some 0.05 to 0.1. This is at the middle of the boundary, and this is x1 over L 0.01. This is close to the triple point. Okay, so we can see that, and we have other things here. Okay, now basically the idea is maybe explain even better in this curve. Okay, so this is a similar kind of analysis, except we are looking at a different boundary. Okay, you can see that sometimes the stress concentration is very small, okay, and sometimes, okay, it's very significant, okay, and sometimes it's compressive, okay. So it depends highly on the microstructural details within the polycrystal. Okay, so this is I'm looking at this boundary. Just now I was looking at a horizontal boundary. Okay, so this is a similar thing. Okay, so I'm not going to bore you with those things. Okay. Now, what is my so we have done the analysis, right? And what I was going to show next is with the microstructural stress as computed by the HLB procedure. Okay, I'm going to analyze on top of that. Okay, the grain boundary sliding. Okay, so this appears back in 1994. Okay, so this is a classical work of I think the metal guys. You have a source, pileup, and then you have the nucleation of a crack. Okay. So here is the problem we analyze. Okay, we have 3 grain boundaries. Okay, we model in this case the sliding. Okay, by the motion of what we call the grain boundary dislocations. Okay, so we have the sources on the grain boundaries. Of course, this, if you want, okay, we can make it statistical. Okay, so we model the motion of the grain boundaries by grain boundary dislocations. Okay. So under the remote loading, we have tau 1, which is the resolved shear stress, tau 2, and tau 3. We can, let me explain the basic idea. The basic idea is under this scenario, okay, these dislocations glide, and they are kind of collide or interact very strongly at the triple junction, and they create some sort of stress concentrations. Okay. So here we have a source of concentration. The source of concentration arises from this strong interaction of dislocations, which pile up around triple point. Okay. In analogy, okay, to the classical work, okay, we have some dislocation piling up against perhaps an obstacle, such as an inclusion. Okay. Here we are piling up against a triple point. Okay. Now we can of course do this. We can analyze this. We can analyze each dislocation, or we can use a continuum or approach. Okay. We can analyze it in terms of dislocation densities. Okay. So we can, based on this model, of course, there's some details. Okay. We can calculate the equilibrium length, and we can calculate whether the length so predicted actually could arise. Okay, because we're going to calculate the energy difference. Okay, the energy of the pileup group, WGR, that is before any crack has initiated, and W is the energy of the cracked, okay, triple junction. Okay, so we need to compare the energy before and the energy after. Of course, the scenario is more likely if the energy of the crack system is lower. Right? With a low energy state, then we can perhaps claim that the nucleation actually can happen. Right? So that is the idea. We can. So I will just show you one result here. Now, what I'm plotting here was the normalized crack length C. I think C is this is not a precursor. This is a prediction. This is the model prediction. Okay? C versus I guess the L is the grain boundary length. Okay, so this is a predicted C over L under 2 assumptions: under the elastic anisotropy assumption and under the grain boundary sliding assumption. Okay, so we predicted that 2A over D, maybe C over L is the order of very small, okay, of the order of 0.05, and if you change some of these parameters, you can get different values. Okay, so I'm not going to show you all of this. Okay. Now, at the same time, I also want to mention the work of Piku and Gupta in 1995. They did analysis. They took a different approach. Okay. What they did was they look at 3 semi-infinite grains, okay, grain 1, 2, and 3, okay, which are with the triple point over here, and they also consider the orientation of these grain boundaries. and I think they call it alpha 1. Okay, so alpha here, okay, alpha 1 80 degrees, and alpha 2 I think is minus 80 degrees, alpha 3 is minus 80 degrees, and something like that. Okay, so this alpha is the grain boundary orientations, and theta over here is, I believe, some sort of a basal plane or c-axis orientation. Okay, so you can actually use the idea of linear elasticity to try and calculate the kind of stress singularity that exists, okay, at the triple junction when you have three dissimilar grains. Okay, dissimilar in the sense that because the elastic anisotropy is of the presence of elastic anisotropy. Okay, and the differently oriented grains. Okay, and they found that the worst case is the singularity exponent, that is stress, whatever stress you apply, sigma, I guess, raised a very small power, minus 0.035. Okay, so that is a singularity, but it's a weak singularity as compared to if you assume a precursor. Right, a precursor is a classical value at n. Okay, it's minus half. Minus half is much stronger than minus 0. This is the worst case scenario. Okay, if you look at other combinations of alpha and theta, you get even weaker, okay, or smaller singularity. So they came to the conclusion that elastic anisotropy cannot be the reason for crack initiation where no cracks existed before. Okay, because this is too weak. Okay. And they also assume grain boundary sliding. Okay, so they went ahead and look at the grain boundary sliding. Okay, and of course their modeling is different. Their modeling approach was different from ours. Okay, basically, I think in a nutshell, okay, this grain boundary sliding. Okay, this pileup of grain not pileup, but this grain boundary sliding was something. Okay, it resembles a mode 2 crack. Okay, it resembles a mode 2 crack. Okay, so if you use the results for a mode 2 crack, there is some correspondence between a mode 2 crack and also the grain boundary sliding. Okay, if this is just a modeling assumption, okay, you can also calculate the nucleation stress. Okay, and this is something I showed you before. The nucleation stress increases with the confinement ratio. Okay, so this is the modeling. The modeling is essentially based on something like a mode 2 crack. Okay, so what did we what can we conclude from here? Okay, we can conclude that whenever we try to predict crack nucleation, okay, if no cracks existed before, okay, we need to have some sort of sufficiently strong singularity. Okay, elastic anisotropy, okay, according to some analysis, one analysis is not strong enough. Okay, but according to my analysis, it could be sufficiently strong. Okay, because okay of the variability of the because the crystal is not a regular hexagon. Okay, you could have two triple points which are close to each other. Okay. So that's it. Okay. Now I don't think I have time to review this. Okay. We also did some work on the influence of having some brine pockets within the crystal. Okay. So I'm going to skip those things. Okay. Now, lastly, I just want to perhaps quickly go over some of the things, possible things that I want to look at. Okay. Now, it has long been known that okay, ice is strongly anisotropic plastically. Okay, so a plastic anisotropy. Okay. So if you look at this crystal, okay, the basal plane represents an easy glide. Okay, and this is the terminal plane, and some other planes, okay, they may be 60 or maybe even 100 times more difficult. okay, for the dislocations to glide. Okay. So there is some inherent strong, okay, anisotropy. So here I'm comparing the elastic anisotropy that I have been looking at, and something that which I think I'm interested in looking at now. Okay, so just now I told you that the difference is very small. Okay, between 1.0318 and 0.8441. Okay, so if you apply a stress of 1 megapascal, the elastic strain incompatibility, okay, the largest possible incompatibility, okay, between the strains under the elastic anisotropy mechanism. Okay, so this is along this crystal is oriented such that the basal plane is perpendicular to it, and this one is perpendicular to the c-axis. Okay, you get something like 1.8, something like 10 minus 5. Okay, the strain incompatibility is order of 10 minus 5. Now, if you look at the plastic deformation, okay, the plastic deformation incompatibility. Okay, I think this is come from here. I forgot the name of the authors. Okay, I should have it somewhere. Okay, Hondo and Higashi. I thought. Okay, which plots, okay, the strain rate, okay, the plastic strain rate, okay, versus the resolved shear stress. Okay, 2 bars maybe 0.2 megapascal, so this is very small stress. Okay, you can see the strain rate, okay, under let's say under the assumption of 0.2 megapascal, okay, the plastic deformation rate is of the order of 10 minus 5. Okay, so we assume something like 2.5 megapascal. And so you have something like 10 minus 5 times 10 seconds. In 10 seconds, you will get a plastic strain incompatibility of the order of something like 1 order higher, okay, than the elastic strain. Okay, so this is the plastic strain incompatibility versus the elastic strain incompatibility. Okay. So the idea is how do we handle this plastic strain incompatibility? Okay, for example, between this crystal and this crystal having different orientations, and this one tries to rotate or shear by something like 0.02 degree, and this one shear this way, and this one shear this way. Okay, it's something like a misfit, okay, between this crystal and this crystal. Okay, and we can perhaps model this in terms of a disclination. A disclination is something a rotational equivalent of a dislocation. Okay, and these disclinations can generate significant stress concentrations. So if I use this model, I will come up with a disclination tripole, one here, and one here. Okay, so basically we have this disclination tripoles. Now, disclination tripoles, they're pretty strong. They possess pretty strong singularities. What do I need to do? I need to calculate the basal shear strain, okay, using some sort of a constituted model for the crystal. I need to model the disclination dipole. I need to calculate the energy in the stress field, and I need to assume what kind of crack would be produced. Okay. So our preliminary calculations show that if you look at this chart over here by Sherwood and Whitworth, okay, this is versus temperature 1000 over T, and this is something like the dislocation velocity per unit stress. Okay, you can see that at minus 10 degrees, something like 4 micrometers per second per megapascal. At a colder temperature, it's much smaller. Okay, 0.02. Okay, so if you have a much smaller dislocation velocity at a higher temperature, okay, then you can see that the strain produced will be much smaller. Okay, so this is a minus 40 degrees. Okay. The shear strain incompatibility would be much smaller than it would be under T minus 10 degrees Celsius. So you need to put higher remote loading in order to produce the same shear strain incompatibility of, let's say, 0.4%. Okay. So it's 2.5 and it's 8.3, roughly something like 3 times. Okay. So I think I'm out of time. So I'll just one or two more slides. Okay. So I would like to look into the plastic anisotropy mechanism, okay, and try to understand the rate dependence, try to understand the grain size dependence, and maybe the temperature dependence, okay. And I also want to look at the kind of cracks that could be generated. I think most of the assumption that we have so far was based on the Griffith crack. Okay, the Griffith crack basically responds, okay, to a remote stress. Whereas we have a xenocrack, okay, we have this opening, which is like something like a raging action, okay, due to some dislocation here or due to a disclination, okay. So we have, so the real crack, I believe, is a composite Griffith and xenocrack, okay. And finally, we may want to look at something like a multi-axial stress state, saline ice, okay. If the ice are already damaged, how would that pre-damaged state affect crack nucleation? And perhaps we want to look at the influence of viscosity. So I think this is all I can say today. Thank you very much.
Hey, any questions? Comments?
Yes.
Yeah, I look at, this is not my field.
Sure.
I'm just looking in general, it looks very fundamental. And so I was thinking that it should be applicable to metallurgy.
To?
Metallurgy.
Metallurgy.
Yeah. So I'm just thinking you use the only thing that will not connect these two fields, because I look at the papers, they all ice. Nobody's talking about metal that you have quoted. So I'm thinking the only difference between the metal and the ice is temperature for the phase change or the crystals, the bonding between the molecules. So I'm just wondering what is more fundamental than a temperature parameter?
Well, I guess, for example, if you look at the plastic deformation of ice, okay, ice basically is hexagonal, right? In ordinary ice is hexagonal, okay. So for example, I discussed the significant elastic and plastic anisotropy between dislocation motion on the basal plane and dislocation motion on some harder planes. Okay, in metals, okay, if you have cubic structures, okay, you have an ample, many slip systems. Okay, so the deformation mechanism is different, I guess. Okay, so you have we are looking at different crystals. Okay, of course you also have hexagonal zinc crystals, for example. Okay, but and also ice exists at very high temperature, under ordinary circumstances. Okay.
John?
Put things in perspective. The discovery by Kyriska et al. In the late 70s is the most significant development in ice mechanics. There hasn't been anything that comes close. Now, we watched Kai talk about many experiments. I mean, the Hobson Choice Ice Island experiments were extremely expensive. But we haven't seen a real lot of fundamental progress. So that's why I juxtaposed a real fundamental presentation right after an ice edge experiment, set of experiments, which is to suggest that if we're going to make progress with the exact types of the ice structure that we can see through the universal stage, we're going to need this. And you're not going to bypass it. You're not going to make fundamental progress without it. And we haven't even got the temperature.
Just to continue, it's I also not also because this workshop organized by John, but I got idea that something is happening today, right? And in particular, but I'd like to stress another say feature of these two talks. All of them are based. For me, it's based on the papers done in 70s, 80s, and beginning of 90s. Is it right?
That's when the money was there.
Yes, and something happened that time, and after that, kind of, okay, I cannot say no, but the intensity of research was kind of damaged. And in some sense, hopefully, so this workshop, we are returning back to that active time.
I actually agree with you. Okay, the last book I published in ice was back in maybe in the late 1990s. Okay, there was a gap of maybe 15, 17 years, okay, on this fundamental work. in ice mechanics. Perhaps John can give us a better assessment of why. Yeah.
Yeah, there was an accelerated research initiative funded by the Office of Naval Research. And the Navy is famous for funding research intensively and then dropping it. And they did that for sea ice. I don't know if they got what they wanted to accomplish, but they got an awful lot of scientists involved, and then it dropped. And yes, I can say I hope that now it's time for this research to come back. I agree. Yeah.
National Oceanographic Center Eugene Axonov, so I'm coming from a different perspective. I'm coming from the climate perspective. I'm a climate researcher, basically. So, Alexander mentioned 1990s when the money was there, in a way. So that's what's funding the research. I think there's a new stream which can be used, or where this development can be used. This is climate research. We're struggling to understand how ice behaves on a large scale, basically. They still don't understand this. We're using models which are becoming reasonably inadequate next 10 years. We are using models which can simulate sea ice dynamics on the scale of hundreds of kilometers or tens of kilometers. But we need much higher resolution for the climate purposes, for the biogeochemistry stuff like this. So we need really fundamental development which tells us how the fraction mechanics can be applied in the climate studies. And I'm sort of reiterating Kai's comment. He's an engineer. He said, I'm looking for a simple solution. Yes, I'm also looking for a simple solution because my model is huge. It has all processes covering biogeochemistry, sometimes sociology, climate research, atmospheric physics. So I need some kind of simple solution which I can plug in the model and use it realistically.
Simple but correct solution.
Yeah.
Okay. I guess perhaps it's a lack of communication between people who work in the more fundamental aspect and people who who work on the practical engineering aspects. Okay, these two, we try to develop models. They can connect the two. We have a microscale model, even a atomistic model, and then we have some mesoscale model, and then we have some large-scale model that most of you were doing. Okay, we have some of this, but this connectivity is a difficult job. It's not easy.
In fact, upscaling is the problem. I mean, when you have looking at small fundamental physical mechanisms, and you want to upscale this to, for example, to sea ice in the field or to observations that you can make from satellite observation and so on. And I think that over the last decades there have been some progress on this, about this upscaling problem. So maybe not so much progress in terms of fundamental ice physics, but well, I don't know, because in terms of friction, for example, there has been a lot of progress also. But,
Okay.
I think that even if in the 80s a lot of work has been done, it's also the case for the last decade.
We'll take one more question. Time. Comment?
Well, thank you for an interesting presentation. I especially like that you referred to kind of old literature. It's not really common today that people read old literature, but I was very heartwarmed that you referred, for example, to Lorne Gould, I mean, grand old man of the Canadian ice research. So that was very nice. And I agree with John actually that this kind of research is really needed if we try to understand the edge contact, what happens. But the problem with the edge contact is when you model it, you have to model the process or understand the process. And these type of studies address parts of that. But it's a synthetic, it must be a synthesis to model the edge process. So that is the problem there. But I have one question. You showed these elastic values of a crystal, anisotropic ice crystal, sort of. And it is very intriguing because you could also express them with Young's modulus and Poisson's ratio.
Yes.
Have you investigated what are the Poisson's ratio values actually for a crystal? I'm just asking this because people always say that Poisson's ratio of ice is 0.3. That's it. But for that kind of crystal, they can be 0.8 or something like that, if I remember correctly.
Basically, this single eye crystal data, okay, I think they were actually experimental data. Okay, and you can, based on this experimental data for the single crystals, you can actually average them, okay, assuming a random distribution of the crystals. Okay. there's some procedure to average them to get a polycrystal, for example, the Young's modulus, okay, and the polycrystal Poisson's ratio. Okay? So this basically we have isotropic overall. Ice is isotropic, so we have two elastic constants. So we need to average this anisotropic, okay, or transversely isotropic single crystals, okay, to give us an E in Young's modulus and Poisson's ratio. Yes.
But columnar ice is also transversely anisotropic.
It's autotropic. Yes.
Of course, I understand the polycrystalline structure, but what I was interested in that, have you looked at Poisson's ratio? Instead of
we did not really. I have not really looked into the details of the Poisson ratio. Okay, but I guess you can do it. I mean, there's no difficulty, okay, in averaging these things. Yeah, we can use any mechanical model under a constant stress assumption or uniform strain assumption. Okay? But the classical work is the Voigt model.
I think we'll have to call it quits here. We got our photographer here, so thank you very much.
Okay, thank you.